All right, there is a relationship between radicals, square roots, cube roots, fourth roots, and exponents. There is this relationship that exists between those things. And that relationship is summed up in this box. The top number of the exponent is the power of the radical. Okay, the top number will always be the power of the radical. In the bottom number of the fraction in the exponent, and m over n is in the exponent, is the root of that expression. Okay, so there's this relationship that says, hey, a fractional exponent is really just this root or radical expression. So examples, I kind of already give you the answer. We're going to walk through those, and then we're going to look at a couple that don't have the answers. What if we have something like x to the 1/2? X to the 1/2 is equal to the square roots of x. Or you're like, well, 1 is the power. You're right, 1 is the power, and that x has a power of 1. Anytime we don't write the exponent, it's understood that there's a 1. What about the 2? The 2 ends up being the root. And with square roots, we actually don't write the root. It's the only root that we actually don't write the number for. But there's actually a understood 2 there. That 2 is part of the root. And you need to know that. Hey, if it's a square root, that number is a 2. We don't write that number, but it is a 2. What about 9 to the 1/2 power? This idea of 9 to the 1/2 power is the same as square root of 9, because the power, the top number, is the exponent, and the bottom number is the root. And what is the square root of 9? 3. So why might we need to know this relationship? Maybe there's an expression that is this really complicated radical expression, and we want to simplify it. And we're having a really hard time simplifying that, leaving it as a radical. What we can do is we can change that to a rational fractional exponent, and then simplifying it might be a little bit easier using the fractional exponents. So something like part C, x to the 2/3. The top number is the power, or the exponent. The bottom number, the 3, is the root. We can also write it this way. The x can be squared, the x can be squared, or the entire expression can be squared. So the squared can actually be outside the radical or inside the radical, and those two expressions are equal. So what does that tell me? That tells me that I can square it before I take the cubed root, or I can take the cubed root first and then square it. It actually doesn't matter which one we do first. And if we're doing these without a calculator, we would try to do whichever one would be easier. Would it be easier to square the number first and then take the cubed roots? Or would it be easier to take the cubed root first? So on a test, what's your question on a test going to look like? Something like this. We got this example. It says x to the 2/5. And you have to rewrite this in radical form. You have to rewrite this as a root. So we're going to have a square root. Not a square root, but a root. And x is going to be inside that root. And then we got to put the 2 and the 5 somewhere. Where's the 2 going to go? The 2 is the exponent. The 2, the top number, is always the exponent. And we can put it inside with the x, or we can put it outside. It doesn't matter where. We can't put it in both places. Inside with the x or outside. And what's the bottom number? The bottom number tells me the root or the index of the root. And that is a 5. That is a 5. What about part B? Same idea. It's really not that hard. So I don't know what you guys heard earlier today, but this is not super complicated today. The A goes inside. Where does the 7 and the 4 go?
7 goes inside, 4 goes
The 7 goes on the right, somewhere on the right, and the 4 goes on the left. The 7 can go outside the radical or inside with the A. It doesn't matter which one. What if part A, instead of just A to the 7/4, what if it was something like 2A to the 7/4? Well, we would have a 2 on the inside. And if you put the 7 on the outside, that's good. But where we need to be careful, if we put the 7 on the inside with the 2A, if we were to put the 7 on the inside with the 2A has to go inside parentheses. Because if you don't put the 2A inside the parentheses, just the A is being raised to the 7th power, not the 2. So those parentheses do matter. All right, what about part C? We're just gonna go the opposite way. I give you a radical, and I want you to write this using exponents. So we have z raised to some power. What's the top number of the exponent gonna be? 2. What's the bottom number of the exponent gonna be? 3. Good. Let's add a number here. Let's put like a 2 in front of the c. I know there's not one there, but let's put one there. And let's put that 2 and c in parentheses. So when I rewrite this in the other form, in the exponential form, the 2 and the c have to be inside the parentheses. If I don't use parentheses, then it's like only the c is inside the radical and the 2 is out front of the radical. That's completely different. The 2 is inside the radical this time. And what is the top number of the fraction going to be? -5. And the bottom number? The bottom number is 3. You'll see at least 2 questions on your test coming from that section. Rewrite as a radical, rewrite as an exponential. Is there really a whole lot more for me to do to teach you that? No, it's just this relationship that we need to know between the 2. All right, so maybe we got stuck with a radical, and maybe we were having a hard time simplifying it, so we changed everything to these fractional exponents. And then we were trying to simplify it using these exponent properties that you guys learned in like 7th or 8th or 9th grade, maybe at some point, that you probably maybe don't remember, but they're there. I'm sure you probably learned them at some point. This first one is called a product of powers, a product like multiplying. So if we multiply something that has the same base, and they have exponents, like x to the a times x to the b, how could we simplify that? What would we do in order to write this as one single expression with just x to a single exponent? What would we do to the exponents? We wouldn't multiply them. A, B would be multiplied. We actually add the exponents. We're actually going to add the exponents. If you want to put that in words, we'll put it in words. Why do we add the exponents? I'm going to give you an example, like pretty much every single property we learned today, and this is why the notes take a little bit longer. Because instead of just saying, okay, we add the exponents, let's move on, I actually show you why we need to add the exponents. So the example we're going to use is x squared times x to the third. What does x squared really mean? X times x. So in parentheses, I'm going to put x times x. That's x squared. Times, what does x to the third really mean? X times x times x. But now we really don't need the parentheses anymore. We really just have x times x times x times x times x. So what would that be equal to? That would be equal to x to the 5th power. Well, where did the adding come from? The adding really came from here. We had 2 of those, and we added 3 more of those. And 2 plus 3 is 5. Now, can we use that property? You've already did this property with questions like x squared x to the third back in like 7th, 8th grade. Today, we're going to focus this on rational exponents, which are numbers that can be written as fractions. So if we have something like this example, the first thing we want to do is take the numbers, the coefficients, and multiply them together. 3 times 4 is 12. We have the same base. We can only add the exponents if the bases are the same. If you have x and you have y, you can't put those together because the bases aren't the same. But in this case, we have b and we have b. The bases are the same. So what are we going to do with the 3 over 2 and the 1 over 4? Not cross multiply. We're going to add them together. We're going to add them together. That brings in another thing. Like, can you use your calculator to add those 2 numbers together in this class? Yes, absolutely. What if you take the SAT and you need to add 2 fractions together? One section on the SAT is no calculator. You can't use a calculator at all, not even like a 4-function calculator. You take calculus, odds are you're not going to get to use a calculator on some part of that course. If it's AP calculus in high school, 2 out of the 4 sections on the AP calculus exam are non-calculator. And there's actually more questions on that section, those 2 sections that are on the other 2 sections that you get to use a calculator. If you take calculus in college, I took calculus in college freshman year, did not get to use a calculator on any test that we took the entire semester. No calculator on the entire test. I needed to know how to add fractions together in calculus. You're like, oh, Mr. Washington, I'm not probably taking the SAT because I'm not going to UGA or Georgia Tech or Georgia College and State University, which are the only three in the state of Georgia that require the SAT for admission. And I'm probably never going to take calculus, Mr. Washington. But maybe you want to be a nurse. Maybe. Like, you got to go to college to be a nurse, right? There's an exam that you have to take in order to become a nurse. Whether it's to get into the nursing program or to be a nurse, I'm not sure. But I used to work as a tutor in college, and this girl came for me for help. She's like, hey, I need help with my nursing entrance exam or my nursing exam or whatever it is to get licensed to be a nurse. And her study book had fractions in it. She could not use a calculator on this test at all. She had to know how to add fractions, multiply fractions, and divide fractions, subtract fractions also without a calculator. So while I'm going to let you use a calculator with this in this class, I'm actually going to show you how to add these together without a calculator, just to refresh your memory. Because at some point, you're going to have to add something like this maybe without a calculator. Maybe without a calculator. How do we add fractions or subtract fractions without a calculator? Yeah, the denominator have to be equal. So the 2 on the left, if we multiply that by 2, it's going to be equal to 4. But if we multiply the bottom by 2, we also have to multiply the top by 2. And why is that? Why do we have to multiply the top and bottom? What is 2 divided by 2? 1. And if we multiply anything by 1, do we change what it equals? No. So we're changing what it looks like, but we're not actually changing what it's equal to. So 2 times 3 is 6. We get 6 over 4 plus 1 over 4. Now, once we get the denominators the same, we add the numerators together, and the denominator does not change. So we get 7 over 4. So while you get to use the calculator in this class, it might be beneficial for you to know how to add fractions without a calculator. Maybe you want to be a nurse. Maybe you want to be a pharmacist. I know that I think for pharmacy school, you got to take a test probably without a calculator that might involve some fractions or something, some dosage charts and things like that. Nurse, same idea. All right, second example, 2 times 4 is 8. What are we going to do to the exponents? We're going to add 3 over 2 plus 4 over 3. Wow, you can use a calculator in this class. Might be helpful to know how to do that without a calculator at some point. Your common denominator this time would be 6. So we would multiply the 3 over 2 times 3. And we would multiply the 4 over 3 times 2. So we get 9 over 6. We end up with 9 over 6 plus 8 over 6. Which is 17 over 6. 17 over 6. All right, we're done with our first property. We add the exponents. If you're multiplying like bases, add the exponents. Whether they're fractions or not, you still add the exponents. All right. Before we go to the negative exponent, we're going to skip over to this one right quick, the quotient of powers. We're going to do that one right quick. We're not going to talk about why. We're not going to do any examples. We're just going to talk about the property. Same idea. What if we had like x to the a, but instead of being multiplied, what if it was being divided? What if it was being divided? What would we do with those exponents? We would subtract those exponents. That is correct. So we're going to subtract the exponents. Keep that in mind. Keep that in mind, because we're going to need to know that in order for me to show you why the negative exponent property works. Okay. We also need to know this one. Anything raised to the 0 power is equal to 1. Anything raised to, we'll come back and do the rest of this in just a second. But the why about what I'm about to explain uses both of these properties. I'll explain these in a minute. All right, cool. The negative exponent property. It says x raised to any negative power is equal to 1 over x raised to the positive power. So a number, any number raised to a negative power is equal to 1 over x to the positive power. So like 2 to the negative third power. would be equal to 1/2 to the positive third power. Like, how's that possible? I'm about to show you how that's possible. And that's the example I'm going to use when we talk about the line. 2 to the negative third power. Let's start there. Everything I do is going to be an equivalent statement leading to 1/2 to the third. And the 2 is arbitrary. The 3 is arbitrary. We could have did x and we could have did negative n, and we could have like proved this for any number, in any exponent. Is negative 3 equal to 0 minus 3? Are those two things equal? Yeah, 0 minus 3 is negative 3. Okay, cool. Using the property down here, the quotient of powers property that we just talked about, if we're subtracting exponents, can I write this way? As a division or a quotient? And the answer there is yes. So now I'm going to write this as a quotient. 2 to the 0 is going to be on top, and 2 to the third is going to be on bottom. We wrote it as a quotient. Okay, cool. I told you we were going to use that property. Okay. What about 2 to the 0? Well, what do we know about any number raised to the 0 power? Any number raised to the 0 power is 1. So what does this equal? This equals 1/2 to the third. 1/2 to the third. Yep. You could actually type 2 to the third. We can figure out what that is. That's 8. So that would equal 1/8. But for the purpose of the property, we're going to leave it like that. What if the exponent in the bottom was negative and we wanted to make it positive? It's going to end up in the numerator. Okay? It's going to end up in the numerator. So expressions are not simplified if they have negative exponents. So all of your classwork today, anything on your quiz or test, all of the exponents have to be positive, and we can make them positive. So if we were to take a problem like x to the negative 2 times 4x to the 3/4, we would get 4x to the negative 2 plus 3/4. We would add the negative 2 and the 3/4 together using that property that we just learned a few minutes ago. That's going to be negative 8/4 plus 3/4, find a common denominator, which is negative 5/4.
Wait, what? I thought it would be 1/x to the 2. How did you get 4x minus 2?
I went ahead and used this property up here. We were adding the exponents. I went ahead and added the exponents together first, because we can add exponents whether they're positive or negative. That doesn't matter. I would probably just use this negative exponent property at the very end. If I add them together.
Pardon the interruption. Teachers, please release the tennis team now. Thank you.
You can go ahead, Andrew. Okay, if you add these exponents together, then if the exponent is still negative, then we can use that negative exponent property.
Oh, so you just didn't do that.
I did not do it at the beginning, because if I added them together, it's possible that it may not have been negative anymore. It could have ended up being positive once I added them together. So then we want to make this exponent a positive exponent. So the 4 has to stay in the numerator. Because the 4, what's technically the exponent on the 4? It's technically a 1. So the only thing that has a negative exponent is the x. So that's the only thing that's going to move to the denominator. So the second example, I would add those exponents together first. Do you have to add them together first? No, I could make that negative exponent positive first, but then I would have to subtract anyway. So I'm going to go ahead and add them together. We get 3 times 4, which is 12. Negative 7 plus 1, they already have common denominator. Negative 7 plus 1 is negative 6/4, which simplifies to negative 3/2. But mathematically, expressions are not simplified if they have negative exponents. So I need to make that exponent positive. The 12 is going to stay on top, and the variable and the 3/2 exponent are going to go to the denominator. And when I move that to the denominator, the exponent becomes positive at that point. All right, cool. Cool.
Yeah, simplify it like that. So it's not a one like, 3 over 10, what's 6/4?
The 6/4 would be okay.
Exactly.
The 6/4 and 3/2 are the same. All right, this quotient of powers, we said, hey, we're gonna subtract the exponents. Why do we subtract the exponents? What if we had something like x to the third over x squared? Simple example. We don't want to go through and we don't want to like write all of these out every single time. So if we can generalize this, x to the third is x times x times x. X squared is x times x. And what can we do with some of those x's? We can cancel them out. X over x is 1. So x over x is 1. We can cancel that out. X over x is 1. We can cancel that out. How many x's are left over? There's 1 left over. It's on the top. So this is equal to x to the first. Well, where did the subtraction come from? Well, we had 3 factors of x on top minus the 2 factors of x on bottom. So how many factors of x are left over? Just 1. We can do the same thing with fractional exponents. So our 2 examples here, we're going to subtract the exponents. In this case, the 4 has to stay in the denominator, and we're going to subtract 1/2 minus 7 over 4. We're going to subtract the 1/2 minus 7 over 4. The 4 stays in the denominator. Just like we multiplied earlier when we had like a 3 and a 4 multiplied together, if we had numbers on top and bottom, we would also simplify those the same way you would simplify those a long time ago when you first learned like fractions. So if I had a 2 on top and a 4 on bottom, I would simplify that to 1 over 2. And then I would still subtract the exponents. So in this case, we subtract. This is really 2 over 4 minus 7 over 4, which is negative 5 over 4. So we get x to the negative 5 over 4 on top, and we get 4 on bottom. When we subtract the exponents, that always goes in the numerator. The top exponent minus the bottom exponent, that always goes in the numerator. If it's negative, though, we need to make it positive. So we're actually going to move the x to the negative 5 over 4 to the denominator with the 4. And it's going to become positive 5 over 4. Well, what does that leave in the numerator? There's like nothing left over, but we have to put something there. We're going to put a 1 there. That is correct. We're going to put the 1 there. So x to the 1/2 over 4x to the 7/4 completely simplified is 1 over 4 x to the 5/4. And remember, x to the 5/4 is just this radical expression, like, hey, that's going to be the 4th root of x to the 5th power. That's really all that represents things. This second example, just like we did before, if 3 over 4 could be simplified, we would simplify that, just like you would simplify any fraction. And then we're still going to subtract the exponents. And I probably wouldn't write this down every single time, 3 over 2 minus 1/3. I probably wouldn't sit here and write that out over and over and over again. I would probably just go ahead and subtract them. 3 over 2 is 9 over 6. 1 over 3 is 2 over 6. And 9 over 6 minus 2 over 6 is 7 over 6, I think. So we get 3a to the 7 over 6 all over 4. It was already positive. We don't change it, because if we were to take that a to the 7 over 6 and put it in the denominator, that exponent would then become a negative exponent. That exponent would become a negative exponent. All right, the zero product property. It works for any number except x equals 0. X equals 0 does not work. We'll talk about why in just a second. What can we say about this? What if we started with like 2 raised to the 0 power? It equals 1, but how do we know it equals 1? I'm going to prove to you that any number raised to the 0 power except 1 or except 0 is equal to 1. Would you say that 2 raised to the 0 would be the same as 2 to the 3 minus 3? 3 minus 3 is 0. We okay with that? All right, we can use this fractional rule that we use, like the division. We're subtracting the exponents. So that's the same as dividing 2 to the 3rd over 2 to the 3rd. What is 2 to the 3rd? 8. What is 2 to the 3rd in the denominator? 8. And if we have the same thing in the numerator and the denominator, what does that equal? That equals 1. So 2 to the 0 is equal 1. That's true for any number except 0. Why is that not true for 0? If we were to use 0 instead of 2, you might get something like 0 to the third over 0 to the third. And what does 0 to the third equal? 0 to the third equals 0. And what can we not do in math with 0? Can't divide by 0, which means 0 cannot be in the denominator. And since this puts 0 in the denominator, we have to exclude it. It works for every number but 0. So what is 0 raised to the 0 power? It's undefined. It's a domain error. You can't compute it. There is no number for 0 raised to 0. So right here, 4r to the 0. Well, what is r to the 0? R to the 0 is just 1. So that numerator is just 4 times 1 all over r to the negative 7 over 4. And we want to make that negative exponent positive. So we're going to move it to the numerator with the 4. And what does that leave in the denominator? We moved everything from the denominator to the numerator. So what's left over in the denominator? There's actually a 1 left over. But if we're dividing by 1, do we need to write that? No, we don't need to write over 1 because it's just the same thing. What about v to the 0? Right here, v to the 0. Can we add the exponents together? We could. But what is 0 plus 3 over 4? It's 3 over 4. But v to the 0 is 1. So we get 1 times 4v to the 3/4, which is just 4v to the 3/4. So we could kind of prove that v to the 0 equals 1 there as well, because 0 plus 3/4 is just 3/4. So we end up with the exact same thing we started with. And if we're multiplying by something and we end up with the exact same thing we started with, what we started with had to be 1. So v to the 0 would have to be 1 in that case. All right, last row today. We'll save the other problems for tomorrow. What if we have an exponent? What if we have an exponent raised to an exponent? A power to a power, or a power of a power. We will multiply the exponents in this case. So this is going to be x to the a times b. So in this case, we are going to multiply the exponents. Why do we multiply the exponents? What if we had x to the third squared? X to the third squared. What really happens? What is really x to the third? That's really x times x times x, right? And how many times are we going to multiply x times x times x by itself? Twice. So I have 2 of these. Well, how many do I have altogether? 6. Well, where's the multiplication? The multiplication is right here. This is 2 groups of 3. And that is the definition of multiplication. 2 groups of 3. How many do you have? 6 altogether. That's 2 times 3 at that point. And we would multiply those exponents. So how do we multiply fractions? Anybody? Maybe you want to go to nursing school. Maybe you want to be a registered nurse. You don't keep it, change it, flip it. That's if you do dividing fractions. Yeah, just straight across. We're going to do the 3 times the 7. We multiply the numerators and we multiply the denominators. So 3 times 7 is 21 and 2 times 4 is 8. The keep it, change it, flip it is dividing.
Okay, so I was right there.
You were close, yes.
Let's see, cross and multiply with.
Cross multiply is when we try to solve a proportional equation. The second equation, b, 3 times 1 is 3, 2 times 4 is 8. 2 times 4 is 8. When do we cross multiply? You could technically, quote unquote, cross multiply when we add fractions, like 1/2 plus 3/4. Some people call this crisscross smiley face. Crisscross smiley face. I don't necessarily like that, but if we're adding, we can crisscross. 1 times 4 is 4, 2 times 3 is 3, and then smiley face. Yeah, you're right. And then 2 times 4 is 8. So we get 4 over 6, or 4 over 8 plus 6 over 8. So if we're adding fractions, crisscross smiley face works, but that doesn't necessarily mean we're using a common denominator. It is a denominator, but 8 would not be the least common denominator in this case. So crisscross smiley face, you can add fractions. Just straight up cross multiply would be something like x over 2 equals 4 over 8. Cross multiply Cross multiply, 8x equals 8, and then you can solve for x. Cross multiply would be an equation, really. That's really the only time we use